Hello and welcome to calculations in this new topic, which is a reflection at curved surfaces. And before we dive deep into the topic, if this is your first time here, just consider subscribing so that wherever I release a new video, you get notified. You may even go ahead and share this video with your friends and discuss some of the concepts that I'm trying to review here. Welcome. So we are going to look at calculations in this topic, which is a reflection at curved surfaces. And as usual, I want to look at some of the main concepts in this topic, not to teach you the topic because I understand you've already been taught this particular topic. I'm just looking at the calculation bit where we deal with the calculations. But for me to go deep into that particular topic, we need to arm ourselves with main concepts. So let's start by looking at what is it that we need to review. We're going to look at, briefly, we are going to look at the types of curved surfaces. We look at definition of terms. We look at rules for ray diagrams. We look at images formed by curved mirrors or curved surfaces. And then we look at the mirror formula. This is where we deal with the calculations when we are looking at the mirror formula. And that is where majority of the challenges come in. But I will start from here to look at the types of curved surfaces that we have. Now, before we look at the reflection at curved surfaces, what is it that we already know in a reflection at plane surfaces? What is a plane surface? It's a mirror whose surface is plane. It's flat. It's not curved. Okay? And this one, you have already looked at it in a reflection at plane mirrors when you looked at rectilinear propagation of light. So, this is the mirror. This is a plane mirror. This is the reflecting surface, and you can see how we represent that. Sometimes we do say this is the plane mirror, M1, M2. There is a ray of light which approaches the plane mirror. We refer to it as the incident ray. At the point where the incident ray strikes the mirror, we call it the point of incidence. Point of incidence. What is it that we draw at the point of incidence? We usually draw a line which makes 90 degrees with the mirror. And that line, this dotted line here, we call it the normal. The normal. The normal is a line drawn at the point of incidence in such a way that it makes 90 degrees with the mirror. Now, the angle between the incident ray and the normal. The angle between the incident ray and the normal. Not the incident ray and the mirror. Be careful about that, because sometimes you're given this angle and then you're asked to calculate the angle of reflection or the angle of incidence, right? So the angle between the incident ray and the normal is called the angle of incidence. When this ray strikes the mirror, it bounces, and the ray which bounces off the mirror is called the reflected ray. Now, the angle between the reflected ray and the normal is called the angle of reflection. And here, of course, we know the first rule for ray diagrams, or the first rule of reflection, the first law of reflection states that the angle of incidence is equal to the angle of reflection. So if this is 30 degrees, this one will also be 30 degrees. If, for example, you are given that the angle that the incident ray makes with the mirror is, let us say, 50 degrees, you should be able to understand that the angle of incidence is 90 minus 50, which gives us 40 degrees. So just be careful here. Where you are given the angle between the incident ray and the mirror, you should be able to get the angle of incidence. That is one of the things that we study in a reflection at plane surfaces. The other thing that we study under reflection at plane surfaces are properties of images formed by plane mirrors. And I hope you can remember them. The size of the image is equal to the size of the object. The image is laterally inverted, although it is upright. It is at the same distance from the mirror as the object is in front of it. And the line joining the image and the object forms 90 degrees with the mirror. So just go through that particular topic, because we'll be talking about a reflection. And when we talk about reflection, there will be those laws of reflection, which I want you to remember. We'll also be talking about properties of images formed by plane curved mirrors. What will happen if you can't remember properties of images formed by plane mirrors? We'll see that it will appear as if it is something new. So I'd like you to review this as we go into this particular topic. After that, we want to look at the types of curved surfaces or curved mirrors. Right? The first one is the concave reflector or concave mirror. Why is it called a concave mirror? It's because the reflecting surface curves inwards. It curves inwards. Remember, for a plane mirror, it was straight, it was plain, but this one is now curved. When the reflecting surface curves inwards, it's called a concave mirror. When the reflecting surface curves outwards, then it's called a convex mirror. That's the first thing that you should be able to understand. And then we are going to look at how each one of them treats rays of light which are close to the principal axis and parallel to each other, right? So let's see how these curved mirrors affect or treat rays of light which are closer to the principal axis and they are parallel to it. Before we look at the terms which we use there, this line here, which is drawn at the center of the mirror, the dotted line here, for both the convex and for the concave mirror, is referred to as the principal axis or the main axis of the mirror. Now, for a concave mirror, when we have a ray of light which is close to the principal axis and parallel to it, you can see this ray is close to it and parallel to it. A ray which is somewhere around here will be very far from the principal axis, but this one is close and parallel to it. Now, when this ray strikes the mirror, it will be reflected through a point which we call the principal focus. You can repeat that process with another ray which is close to it, this one, just close to this one, so it is close to the principal axis also and parallel to it. Again, that ray will be reflected through this point which is called the principal focus. We're going to define that term, the point at which all rays which were close to each other and parallel to the principal axis converge after reflection. We can repeat that process with this other side here, just below the principal axis, and that ray also is reflected through the principal focus. So, how about for a convex reflector or for a convex mirror? This is what happens. A ray of light which is close to the principal axis and parallel to it is reflected as if it is diverging from this point here. All of them are reflected. Even this one, it is reflected as if it is coming from this point. This point is referred to as the principal focus for the convex mirror. So here, the rays actually converge. Here, they diverge as if they are coming from this point, or they diverge from this point, right? So, I identify the incident ray and the reflected ray. Now, again, the laws of reflection, they are followed here, because at this particular point, we've got, at this point, we can draw the normal, which happens to pass through the center of curvature. And if we draw a line there, you'll be able to see that the angle of incidence will be equal to the angle of reflection. That one is something which you dealt with when you looked at this particular topic in details. So, having introduced some of the terms that help us in this study, let's look at the other terms. And one of them is the aperture of the mirror. This plane here from X to Y is called the aperture of the mirror. The pole is the center of the mirror. It is at this particular point. This point here is called the pole of the mirror. It is a point at the center of the mirror. How about the center of curvature? The center of curvature of the mirror is the center of the sphere of which the mirror is part. Remember that these curved mirrors, they are part of a sphere. That sphere has a radius. So the radius of that sphere is the same as the radius of, if we cut a small patch on the sphere and make a reflecting surface out of it, you will find that that patch will be part of the sphere, and that sphere had a radius. So the center of curvature is the center of the sphere from which the mirror was obtained. So the center C, the center of curvature C of the sphere, is the center of the sphere of which the mirror is part. In the case of a concave mirror, the center of curvature is in front of the mirror, while in a convex mirror, it's obviously behind, because here we'll have to shade the inside if it is a convex mirror. We have already seen that. The other term that we want to define is the principal axis. I've already mentioned the principal axis or the main axis. It is a line drawn through the pole of the mirror and the center of curvature. This line, which is drawn through the pole of the mirror and the center of curvature, this dotted line here is called the principal axis. It's also called the main axis. The other term is the principal focus. For a concave mirror, it is the point at which all rays which were parallel and close to the principal axis converge after reflection. All of them converge at that point, and we have already seen that. For a convex mirror, the principal focus is the point at which all rays parallel and close to the principal axis appear to diverge from. They appear to diverge from that particular point after reflection by the mirror. There is some more information here about the principal focus. The principal focus of a concave mirror is a real focus. That is, reflected rays actually pass through it. Reflected rays actually pass through it. And we have already seen that. Let's just review that. You can see that for a concave mirror, this principal focus here, the reflected rays, when this ray strikes the mirror, it's reflected through that point. This other ray are reflected through the same point. So it is a really principal focus because reflected rays actually pass through it. But when we look at the principal focus of a convex mirror, it is a virtual principal focus because reflected rays do not actually pass through it. This is the incident ray and this is the reflected ray. The rays only appear to diverge from that point, but they don't actually pass through it. So the difference between a real principal focus and a virtual principal focus. For a real principal focus, reflected rays actually pass through it. A virtual principal focus, reflected rays just appear to diverge from it. Notice that particular difference there. Let's continue and we look at the other one, the focal plane of the mirror. The focal plane of the mirror is a plane perpendicular to the principal axis and passes through the principal focus. Where is the principal focus? It is here. By the way, the principal focus divides the radius of curvature exactly into two. I'm going to mention that briefly. So, there is this plane here which is perpendicular to the principal focus and it passes through F. This plane here, this plane which is perpendicular to the principal axis and it is drawn at the principal focus is called the focal plane. The focal plane. Okay, the focal plane is a plane perpendicular to the principal axis and passes through the principal focus. Parallel rays which are not parallel to the principal axis would converge at a point on the focal plane. Rays which are parallel to each other. Let me just show you that one from our textbook here. By the way, we can draw the reflecting surface as being straight, as if it is a plane mirror, and then we draw the symbol for a concave mirror here. That one becomes a concave reflector. So you can see these two rays, they are parallel to each other, but they are not parallel to the principal axis. When they are reflected by the concave mirror, they will converge at the focal point. They will converge at the focal point. That one is so important. Let's continue with our PowerPoint slides. So we have already seen these parallel rays which are not parallel to the principal axis would converge at a point on the focal plane. The radius of curvature, R, is the radius of the sphere of which the mirror is part. Remember, this one is part of a sphere, and that sphere had a radius from the center all the way to the surface here. That is the radius. The radius PC is called the radius of curvature. That radius is also can be drawn from any other point, maybe here, maybe here, maybe here, so long as it is some sort of radius for this particular arc. So the radius of curvature of the mirror is the radius of the sphere of which the mirror is part. Let's look at the focal length. It is the distance from the pole of the mirror to its principal focus. This is the pole of the mirror to the principal focus. This distance here is called the focal length. Since F divides PC exactly into 2, since F is exactly at the center of PC, since F divides the radius of curvature exactly into 2, then the focal length, this one is a focal length, this one is also the length of a focal length, right? It is equal to this other length. But by definition, the focal length is the distance from the principal focus to the pole of the mirror. The distance from the principal focus to the pole of the mirror. So this distance here, if it is 2 centimeters, the focal length is 2 centimeters. However, this one will also be 2 centimeters because that means the radius of curvature is 4 centimeters. These are some of the terms which I would like to review because I would be using them from time to time. They'll be mentioned even in problem solving. So you need to understand what they are. Now let's look at rules for ray diagrams. After that, we will go into the mirror formula and into problem solving. Which is the first rule? We have just seen, if it is, for example, a concave mirror, we have a ray of light which is close to the principal axis and parallel to it. It will be reflected through the principal focus. So this blue line shows that first rule as applied to concave mirrors. So a ray of light which is parallel to the principal focus and close to it is reflected through the principal focus. Rule number 2 is the reverse of that. However, I've drawn it from a different position. It really does not matter whether I use the principle of reversibility of light and just trace that path and back like that, or use some other point. A ray of light which passes through the principal focus will be reflected parallel to the principal axis. It is the reverse of rule number 1. Rule number 3. A ray of light which passes through the center of curvature, through C, will be reflected through the same point, through C. Let's look at the same rules but applied now to convex mirrors. The first one was a ray of light which is parallel to the principal axis and close to it is reflected as if it is coming from F, from the principal focus. Number 2, a ray of light which appears as if it wants to pass through F, this one is a straight line, a ray of light which passes through F or appears to pass through F will be reflected parallel to the axis. And finally, a ray of light which appears to pass through C, and by the way, don't confuse F and C. They are totally different according to the definition. C is exactly between this point. F is exactly between C and B. A ray of light which appears to pass through C, is reflected as if it is coming from C. with those three rules, now we can look at the ray diagrams. So in the next video, we are going to look at now the actual calculations, starting from the ray diagrams all the way to using the mirror formula. Don't miss that video, which will be coming in a short moment. Bye-bye.